Hello again. The objectives of this podcast is to complete our review of the practice unit exam for chemical bonding to correct misunderstandings. Now let's take a look at number 14. It states the abnormally high boiling point of HF, hydrogen fluoride, as compared to HCl, hydrogen chloride, is primarily due to intermolecular forces of attraction called intermolecular. This is a statement that gives students fits. Intermolecular requires you to think about separate molecules and how they would relate to each other. So, for instance, HF, how one HF might relate to another HF, and how one HCl might relate to a different HCl. Now, let's dissect the question. It says the abnormally high boiling point of HF. Now, why is HF abnormally high in comparison to HCl? Now, that stems from the reality that fluorine is highly electronegative, meaning that it is going to be a polar bond between hydrogen and fluorine, where the fluorine is very negative. It takes the electrons, I shouldn't say takes, it shares the electrons unequally with hydrogen, so much that hydrogen becomes slightly positive while fluorine slightly negative. So that would happen to the neighboring molecule as well. Slightly positive, slightly negative. And as a result, there will be a connection, an intermolecular force between the hydrogen of one molecule and the fluorine of its neighbor, holding them together, so it requires a great deal of energy to break the bonds so that they go from the liquid state and fly apart from each other to the gas state. And that just does not exist between this hydrogen and this chlorine. Those electronegativity differences are not strong enough to make that happen. So, the answer for number 14 is hydrogen bonds. Now let's take a look at some other choices though. Network bonds. We did not discuss network bonds whatsoever, nor have we discussed the concept of electrovalent forces or something known as van der Waals forces. So by process of elimination alone, you should have gotten yourself two hydrogen bonds. But there's the explanation, and you might be responsible for giving it. Question 15. Molecules. Now I'm going to stop right there. As stated earlier, once you hear the word molecule, you must think of a covalent bonding situation. But it says molecules in a sample of NH3 liquid, that's ammonia, are closely held together by intermolecular forces. Intermolecular forces. We must have NH3 next to neighboring NH3s. Now what's going to hold this one to that one? So here are our choices. Choice 1. Existing between ions. Well, nonmetal, 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 nonmetal. No ions at all present. Next. Existing between electrons. Oh, electrons being shared between two different molecules? No. If they were being shared between these, well, if they were being shared between the elements in this one and the elements in this one, they would be held together and be a compound. 3. Caused by different numbers of neutrons. Neutrons and bonding? Never discussed that, although that was an answer that I saw a few times. The neutrons really destroys this one. Now choice 4, let's examine it for the cause. Caused by unequal charge distribution. Absolutely, because within that molecule of ammonia, we would have nitrogen, hydrogen, 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 a bond, a bond, a bond, an unpaired share of electrons. We would have an unequal distribution of charges within that molecule, and a neighboring ammonia would be impacted by it. So this would be slightly positive, where this is slightly negative, and there would be an attractive force between them, an intermolecular force of attraction. Number 16. Which structural formula represents a non-polar symmetrical molecule? So who cares about the individual bonds being polar? Okay, because in each one of these, that is the case. Every single bond is polar here. So, for choice 1, we have 1, 2 polar bonds. For choice 3, we have 1 polar bond. In choice 4, we have 3 separate polar bonds. And in choice 2, we have 4 separate polar bonds. But the question talks about the entire molecule being nonpolar because it is symmetrical. So which one of these choices shows symmetry? Choice 2. Question 17. Which substance contains bonds that involve the transfer of electrons from one atom to another? So we're not sharing electrons, it's a complete transfer. In this case, we are looking for ions. So we have 3 scenarios where we can build ionic bonds, and that is when we have a metal bonding to a nonmetal. The nonmetal is so highly electronegative it actually captures an electron from the metal. We could also have a positively charged metal bonding with a polyatomic ion, and we could have a positively charged polyatomic ion bonding with a nonmetal. Oh, in reality, we could also have a fourth. We could have a positively charged polyatomic ion bonding with a negatively charged polyatomic ion. Each one of these, you would witness a transfer of an electron from one substance or element to another. So let's inspect these. Well, we are looking for anything but nonmetal to nonmetal or metal to metal. In the case of choice 1, carbon and oxygen. Here we have carbon and oxygen, both nonmetals. They share electrons. Choice 2, nitrogen and hydrogen. Nitrogen, nonmetal. Hydrogen, although on the left side of the periodic table, is a nonmetal. That's covalent bonding. Next we have potassium and bromine. There's potassium, metal. There's bromine, nonmetal. It is a consideration. Let's put a check mark next to it. And lastly, chlorine to chlorine, nonmetal to nonmetal. Once again, it must be a covalent bond. It's out of the picture. Answer is 3. Now, here's our last question. Which compound contains both ionic and covalent bonds? From previous questions, you should have ascertained that ammonia is NH3. Methane we didn't discuss. You didn't even see hints of it earlier, so you should have considered it not to be an option. But let me tell you, methane is CH4. Sodium nitrate, the way the compounds are named should give you some hints. And number 4 is potassium chloride. So we're looking for ionic bonds and covalent bonds. Let's take a look at ammonia. Sorry, that's ammonia. Ammonia is both nitrogen and hydrogen together. We have hydrogen. There it is, hydrogen, nonmetal, to nitrogen, nonmetal. Only covalent bonds are present here. This cannot be a choice. Methane, carbon and hydrogen. Carbon, hydrogen. Both nonmetals, only covalent bonds, not a choice. Sodium nitrate. Well, let's put that aside for just a moment and look at potassium chloride. Here we have potassium and chlorine. Metal to nonmetal, we will only see a transfer of electrons from potassium. One electron will move from potassium over to chlorine. We will only see an ionic bond there. Let's take a closer look now at sodium nitrate. Sodium is Na. The fact that we have the word nitrate, not nitride, well, should make you suspicious of a polyatomic ion. To confirm, we go to table E. Inspect. We're looking for nitrate. Nitrate. Where are you? There it is. Nitrate. Trying to get my pointer. There is nitrate right there. NO3. So let's put that down. In fact, I'll put it down as another color. NO3 negative. While the sodium had a positive 1 charge. Now, what is responsible for holding the nitrogen to the oxygen, nonmetal to nonmetal? Right here, we would have a covalent bond. Funny looking D. And what is responsible for holding the nitrate and the sodium together, seeing that we have a transfer of electrons? Well, that is an ionic bond right here. And that answers our question. We are looking for an ionic and a covalent bond. Our choice must be choice 3. Thank you very much. I hope this review is successful in helping you with your actual unit exam. Good night.